here we have a pretty innocuous graph of some sort of a function, and we want to construct its slope graph. So we're going to have the graph of the function here. We're going to have the graph of the slope function here. Now, the graph, the function is going to be y equals f of x. The slope function is going to be y equals f prime of x. Okay, the prime there indicates that the values of the function we're going to do, that we're going to graph here, should be approximately equal to the values of the slopes on this graph. Now, the graph is unlabeled, so we don't know what numbers go with anything, and we're not going to use numbers to construct this graph. Totally unnecessary. Now, once we know what the graph represents and have a numerical representation, in other words, once we scale this graph will also have a scale determined by the scale of this graph. But to construct the slope graph, we don't need any of that. We don't need any scaling. Now, what I'm going to do first is I'm simply going to divide this graph into equal regions, that involve what should be equal changes in the x value, to equal x intervals. And that region is a little too big, but you get the idea. Okay, then I want to sketch tangent lines at a series of points. And they don't have to necessarily correspond to the lines that I've got here. I could sketch a tangent line here. I could sketch another tangent line here. I could sketch another one here, and another one maybe here. So I'm going to do that. Doesn't matter. The locations of these points is unrelated to these vertical lines indicating the x region. So I'm going to construct a tangent line here, and I want to be sure that the tangent line crosses at least two of these lines, two of the vertical lines that I constructed. So this tangent line is extended to cross this vertical line and this vertical line. You'll see why in a minute, and it should all make sense. Okay, now I construct a tangent line here, and I'm not sure I'm really constructing in the compass and straight edge sense, but I pretty much am. And of course, this one crosses two of these vertical lines, but that's harmless. Then I'm going to construct one here. And I'm going to construct one here. Now, if I've got a nice smooth curve, it should be easy to determine lines whose slopes are equal to the slope of the tangent line. Notice that some of these points, some of these tangent lines, well, actually I did a pretty good job on these, but if the tangent line's a little high or low, that's really kind of harmless. But what we definitely don't want is, we don't want the tangent line not to be, or the line that we construct not to be parallel to the line, which would be tangent to the circle. We want it to be close to the curve, that we don't worry too much about whether we're a little high or a little low, because really all we're looking at is the slope. So I can then, for each of these lines, construct a right triangle. And of course I could construct this with compass and straight edge. Okay, there's a right triangle on the first line. Okay, so I'm going to kind of mark this point in purple just so we can distinguish. So I'm going to actually fill this triangle in. And this at least represents a triangle that we could have actually constructed. Okay, then for this tangent line, I'm going to pick, and this tangent line crosses three of the vertical lines, but I'm going to pick the point where it crosses this line and the point where it crosses this line, and I'm going to sketch the triangle I would construct for this line. Okay, then do the same for this tangent line. So I'm going to use this point and this point on the tangent line and construct or sketch the triangle that I would construct. And then for this tangent line, I'll use this point and this point. Not doing a very good job of sketching a good right triangle, but there it is. Okay, now, without too much comment, I'm just going to say that the graph being unscaled, and I'll elaborate on this a little bit in a separate video. Since the graph is unscaled, I can simply take each of these rises, and this is because they all have the same run, and use the rises to represent the y value for the slope graph. Okay, so at the first point, and the x-coordinate of that point is here, so we're going to go ahead and dot that down to here. I'm going to have a line segment of this length. So I could actually construct that line segment. And at the top of that line segment will be a point on my slope graph. Okay? Now, corresponding to this point on my graph, I obtained this triangle with this rise. So I'm going to take the coordinate of this point and drop it down here, take this rise, construct a line segment of that length, and a point on my graph will be here. Then, next tangent line was at this point. So I'm going to use the length of this segment, and that'll be constructed down here, giving me still another point on the graph. And finally, for the tangent line at this point, I use the length of this segment, which is about like so, and I get this point. So that my slope graph could be a line or a curve, smooth curve, through these points. Now, I can actually see the curvature of the slope graph a little better if I simply double the coordinates of all these points. Since this graph is unscaled, I'm free to do that. I still get the shape of the slope graph, and it can still be scaled to represent the accurate graph. Okay, so I just double all of these x values, and now I sketch a curve to represent my slope graph. Now, I haven't gone into detail about why this works, why I can simply use these rises, although that was discussed in class. I'll do that momentarily, but in another video. And I'm going to leave that without comment for the moment. We'll continue this in another video just to justify what we did. But this method will construct a valid slope graph. And again, once the original graph is scaled, that implies a scale for the slopes, and that then implies a scale for this graph.